So I realized this morning that there is actually very little about dimension 4 on the slides, but the slides are static, so I will have to talk about the ones that are here. So I begin with some background. So the problem I'm interested in here is that of seek POVMs, and you probably know what that is. We can begin by defining an equiangular tight frame. I'm always in a finite dimensional Hilbert space, dimension D. When I say D, it means the dimension. We're looking for a collection of unit vectors that form a resolution of the identity, and the modulus square of the mutual scalar product should be a constant. It's quite easy to prove that the number of vectors in such a collection has to lie between D and D squared. If it's equal to D, it's very important. It's an orthonormal basis. If you reach the maximum, it's a seek or a seek POVM. And since the minimum is very important, I expect the maximum to be important too. And standard conjectures, when people started this, is that these things exist in any dimension. This has been verified numerically in more than 200 dimensions. And another important conjecture says that there are always orbits under a Heisenberg group. That is another piece of motivation. Perhaps some of the mathematicians here don't know Arthur Eddington, but he was a very famous physicist, and he said that at or nearly at the roots of everything in the physical world lies a Heisenberg group. So that presumably makes these things important. The Heisenberg group I will be using is this one, which was considered by Weil in his famous book. So it's generated by 3 elements of order D. Omega belongs to the center of the group and can be represented as a root of unity. And then the general group element looks like this. One important fact about these groups, I will come back in the talk, is that if you look at the Heisenberg group, it has a unique irreducible representation, I should say, in dimension D, once you fix this. So the unitary representation is unique and tied to the dimension D. If the dimension is composite, this group splits as a direct product. That will be important, provided that the factors are relatively prime. I should say that my chairman is interested in seeks represented that are orbits under a different Heisenberg group. My seeks will be orbits under this, and in my opinion, more work should be done on the other groups, even more than you have done, I think. There's another group that is important in this context, which is called the Clifford group. It's a normalizer of the Heisenberg group within the unitary group. So it's a collection of unitaries that permute the elements in this group. If you apply such a unitary to a seek that you have found, the result will be another unitarily equivalent seek, or exceptionally, it will be the same seek. If that happens, you say that the seek has a symmetry. And a conjecture going back to Gerhard Sauner says that every seek generated in this way has a symmetry of at least order 3 from the Clifford group. That's beginning. Now, it's nice that these things are orbits under a group, because that means you can define the seek not by listing all the d squared vectors, but just listing a single vector called the fiducial vector, and then you act on that with the group. There is a catch with that, assuming I can get the next slide, which I cannot. Well, the first catch is that I can't really get to the next slide, but that can probably be arranged by some clever means.
This one.
I somehow. You mean it works now? Well, anyway, here's the catch. The fiducial vectors that you get tend to look rather disgusting, I may say. So this thing, which is a fiducial vector for a seek in dimension 6, at the time it was the highest dimension in which an exact solution was known. It's taken from a paper by Marcus called Seek POVMs and MUBs in dimension 6, if I remember right. And Carl and I and Wojtek Rusta read that paper with great enthusiasm because there were interesting things about MUBs. We looked briefly at this and decided that we'll never work on these things. That was a wrong reaction, actually. What we should have said, looking at this, is that the square root of 21 is all over the place. And some years later, after looking at many more examples, Marcus Appleby, Julia Appleby, and Gerhard Zauner realized that the correct reaction to this is that the square root of d plus 1 times d minus 3 is always in there in every seq. And that leads to this. Exactly what's up there, you'll never know. But that led to, yeah, so there's a key paper, partly obscured here, by Appleby, Flamea, McConnell, and Yard, 2016. This is sort of a game changer, because they figured out what number fields are relevant to seqs. That's a stupid name for physicists. I have to tell you that there's a much better name in German. These are number fields, or Körper in German. So for every seq, the square free part of d plus 1 times d minus 3 always comes in. D is assumed to be larger than 3 here. And the numbers needed to write down seqs in the standard representation of the Heisenberg group always use extensions of the real quadratic field obtained by adding the square root of that thing to the rationals. And then you extend that with, and the extension is supposed to have an abelian Galois group. That's the first number theoretical result. In this paper, they were being much more precise. In every dimension, there's a minimal seq, which is constructed using a ray class field with conductor D. I have this in quote because I'm not going to explain what this is, but the main point is that these things are known to mathematicians, and computer programs like Magma have algorithms that will produce them for you if you specify the quadratic field and if you specify the conductor D, which happens to be the dimension. So that means we know the number fields that are relevant here. Actually, in almost every dimension, there are other seqs that use somewhat larger number fields. That story is supposed to have been more or less completed by Kopp and Lagarius, but they never published, so I don't know anything about it. Yeah, you've told me this for 3 years. Yeah, this was supposed to come out in 2018, and Marcus always says the same thing. Will come soon.
There was pandemic. So.
Yeah, whatever. That means that we know what sort of problem it is. It's sort of similar to the problem of constructing regular polygons in the plane. As you will recall, you can get the exact expressions for the corners of regular polygons by using the cyclotomic fields, so what you get by extending the rationals by the roots of unity. You form this function here, and then you evaluate this function at rational points, and you get the corners of the polygon. Our problem should be sort of similar to this, but the catch is that the number fields that we need for the problem are not well understood. That's actually part of Hilbert's 12th problem, to understand these number fields as well as people understand the cyclotomic fields. So although this tells you where to go, it's not a complete solution. What's on the next? Yeah. So the first thing that happens now, because we related seqs in dimension D to the square free part of this thing, is that lots of dimensions turn out to be number theoretically related to each other. So if you fix the real quadratic field and you solve this equation for D, you get all the dimensions that are number theoretically related to this quadratic field here. And it turns out that there is always an infinite number of solutions. So if you fix square root of 2 to begin with, here's the sequence. D1 is 7, D2 is 35, then comes, yeah. For if you fix D to be 3, well, here's the sequence. If you fix D to be 5, here's the sequence. I've obviously listed only parts of the sequences. The dimensions I've listed are dimensions where the seqs have been unknown in exact form, with 2 exceptions. 2208 is known only numerically, and it's interesting that this is the largest dimension in which a numerical search for a seq has been successful. So higher than that, it seems you can't really go. The reason why Andrew Scott and Marcus Grassel were able to do this is that the symmetries of the seeks actually increase as you move up this sequence. So it's 3 times the position in the sequence. So the symmetry here is high. This is also in brackets because it's not known, but I am very keen to know it, so I put it in there. There are more detailed number theoretical relations here. So this is what's known as a field inclusion lattice. It's the same for all the sequences. So what this tells you is that the number field needed to construct the seek in the first entry, D1, is a subfield of that in second, the fourth, the eighth. It's also a subfield of the seek you need in the fifth and the seventh and the 13th, etc. It's not, however, a subfield of the third, and it's not the subfield of the 9th. So if your ambition is to simplify the problem by focusing on perhaps some sort of subseek, instead of doing seeks in every dimension, maybe your more limited object would be to find an infinite sequence of dimensions and solve the seek existence problem only in that infinite sequence. Then you should probably not go for these sequences because the number theoretical relations between the different dimensions are not all that clear. So my next thing is, so how do we select a suitable infinite sequence where we can have some hope of solving the seek existence problem? And the first suggestion that suggests itself is let's move straight up in this field inclusion diagrams. So suppose I pick the subsequence here consisting of the first, the second, the fourth, the eighth, or for that matter, the 7th, the 14th, whatever. The position in the sequence is always doubling along the vertical lines here. It turns out that the dimensions along such a vertical subsequence are very simply related. So here's an example. I'm going to relabel re-index the dimensions in this sequence. So instead of D1, D2, D4, D8, I talk about D1, D2. I mean, I just change the labels here. Then the dimensions that occur here are related by this simple recursion relation. And it turns out when you start looking at seeks in dimension in the first, in the second, in the third, etc. entry, you will find that if you know the seek in, let's say, the third, in this one, then you get, we cannot really use this seek to define the seek in the next, but we get lots of partial information about the seek in the next dimension. And I should mention that the Hadamard matrices are not far beneath the surface here. If you're interested, you can look at these papers. Yeah, they are complex. Yes, I apologize to the part of the audience, presumably prefers real ones. So a particularly interesting subsequence is the one that starts 5, 15, 195, 37,635, etc. The interesting thing about this subsequence is that you can make the numbers that appear in the seek fiducials look a lot nicer than they typically do. So here are the first, we also know the third, first, second, and third. The third is also easy. It turns out that if you use a suitable basis in Hilbert space, which is adapted to the symmetries, which are growing as you go up the sequence, then you can express your seek. So these basis vectors are computed in a routine fashion. They look a bit ugly, but they are computed in a routine fashion. And then the seeks look really very nice expressed in this basis. There are some absolute values there, which are simple. And then there are some phase factors. And these phase factors are always roots, sometimes of rather high order, of what I call Pythagorean phase factors. So they constructed using Egyptian triangles. And there are a few of those. And with those, you can write down these 3 seek fiducials very simply. But we don't really know what these numbers really are, so to say, from the ray class point of view. So we can't really guess the next dimension, what it looks like in the next dimension. But my hope would be that if we could produce this thing numerically, so we could, then we could work out a similar expression, and then maybe we would figure out what these numbers actually are. As I was saying, we have partial information about the next entry in the sequence, but we still need to do a numerical search over 98 free parameters to find it, and we haven't done that. That was the first infinite sequence, and here comes the second, which has produced more results. So here we focus on dimensions for some reason that are of the form n squared plus 3, which means that we're going to use different real quadratic fields in the sequence. So the D, capital D, is not fixed. The reason for focusing on these dimensions is that this sequence appears, well, we think that they include, this is numerically supported, so to say, we think that they include every seat that has not only a unitary symmetry from the Clifford group, but also an anti-unitary symmetry from the extended group. And the anti-unitary symmetry turns out to be very illuminating. If you assume that you have a seq which has an anti-unitary symmetry, you can argue that it should take this particular form. So you take the vector, you take its complex conjugate, that's the anti-unitary part, and then you apply the parity matrix, the Fourier matrix square, to the vector, to the conjugated vector, and you get the vector back again. So this is what we think the symmetries look like. Once you know that, you will realize that the seq fiducial is going to be almost flat. That is to say, with one exception, all the entries have the same modulus, so you can, they're complex, so you can always write it in this form then. This has been known for some time. It's based on a paper by Einstein, 1914, although he wasn't interested in seq specifically. So what can we say about this infinite sequence? Well, we think we know what these phase factors that occur in the fiducial actually are from the number theoretical point of view. And when I say we think, the argument, whoops, what I mean is that we've tested this hypothesis in by now 48 different dimensions, and it always works. So I'm quite confident that we actually know what these phase factors are. They are square roots of something called Stark units in a subfield of the Ray class field you need to construct the seq. And the fact that it's in a subfield is very significant because that means that the computational problem shrinks dramatically. Stark units is something I'm not going to explain either, but Stark units in the cyclotomic field, you know, they are just the roots of unity. And this is a partly conjectural generalization of that to particular to real quadratic extensions of real quadratic fields. So these things, there are ways to calculate the Stark units from number theory or from L functions more specifically, and then we put them in the seq. Then we put them in the vector and check whether it's a seq. That's the long and the short of it. The details are a bit more complicated. So here's again a field inclusion diagram. This field is a subfield of this, is a subfield of this, is a subfield of this. So we start with a real quadratic field that we get from the particular dimension we're in. Then we go to something which is called the class field, which is a complication I'm going to slur over. And that is a subfield actually of two small Ray class fields. This one, this small, and then if you extend these small Ray class fields with the, to include the cyclotomic field as a subfield, you get the full Ray class field with conductor D that you need to construct the full seq. Our procedure is to take one of these small Ray class fields and compute real Stark units here according to the recipe provided by number theory. Then, for some funny reason, we want complex phase factors, so we have to make a Galois transformation to get to the other small Ray class field. And in the process, the real Stark units turn into phase factors, namely precisely the phase factors that we want to put into our seq after taking the square roots. So here we construct the fiducial vector, and then when we apply the Heisenberg group to get the full seq, we get the roots of unity in, we get the full ray class field and the full seek sits here. And then it's only a question of checking that we actually got the seek. And okay, the checking is mostly numerical, but we did carry this procedure through in 48 cases. And the highest dimensions in which we, perhaps I should make a little remark here. If you look at the list of my collaborators, you may wonder who did this calculation. Well, here are the highest dimensions. We obtained my personal record. It's actually 5,779. You'll have to guess who did the others. Anyway, the highest dimensions in which this procedure works are those that we have tested. So we go up to 39,604. That's the highest. I should say, because there are various cases missing here, that the difficulties in carrying through this procedure doesn't grow monotonically with the dimension. This has a lot, there are lots of complications that make certain dimensions easier than others. This has a lot to do with this complication here that I was slurring over. But anyway, we have 48 examples, so we're pretty sure that this works. The larger perspective on this means that we are now in a position to actually compute seeks from number theory in high dimensions without any numerical crutches. I mean, we don't have to rely on a numerically known seek. One can then show that if you take the Weil-Heisenberg group elements and calculate these overlaps, well, because it's a seek, it has to take this form. The absolute value is determined by the seek condition. And then there's a phase factor here. These phase factors themselves are start units or start units squared in the full ray class field. An exception, they're start units in a something. So that basically means that in order to prove that rather than checking, that our procedure always works, we can convert our procedure into a set of identities for start units in related ray class fields. So the task of proving seek existence is turned into a problem of proving various identities for start units. I know plenty of identities for roots of unity. I don't know many of those. So this is very much an undone project. I should also mention that there is an alternative approach to that also uses start units, and I think Marcus will talk about this. In that case, which is something that has been pushed by Appleby, Flamia, and Kopp, they construct seeks directly from these overlap phases, which they can in principle calculate if you assume that they are start units squared. Their procedure applies to all seeks in every dimension, but it's computationally much harder. Marcus will give details later. And now I'll say something about the groups that enter this problem to explain why the procedure works. I'm coming to the topic of my talk, but only towards the end. Sorry, I made these slides and I didn't realize how much background I was putting in. So how does the Heisenberg group work? And here I will focus, although it doesn't really show, on the special case of prime dimensions, because that's simpler to explain. So as I was saying, there's a unique irreducible representation of these groups, and Weil's choice to get the really explicit representation as matrices was, let's diagonalize the cyclic subgroup of the group, with the cyclic subgroup then as order. So basically you would diagonalize this generator Z, and then Z squared, etc. is also diagonal. And that fixes the representation completely. Now there are P+1 such subgroups in prime dimensions, so the Heisenberg group. So here's for the dimension 3, here's for dimension 5, when there are 6 cyclic subgroups. Now I also told you that seeks have a symmetry of order 3 at least. This is called the Sauner symmetry. And the symmetry, remember that these group elements permute the elements in the Heisenberg group. That means that they also have to permute the cyclic subgroups. So here, in dimension 3, you can find such a symmetry operator which leaves this cyclic subgroup invariant and transforms the other into each other. Now, if the dimension is 2 mod 3, then there are then the number of cyclic subgroups is divisible by 3. So the cyclic subgroups form multiples of 3. So the Sauner symmetry works by transforming these cyclic subgroups into each other and these cyclic subgroups into each other. However, if the dimension is 1 mod 3, then there are 3k plus 2 cyclic subgroups, which means that there has to occur 2 cyclic subgroups that transform into themselves under the symmetry. And that tells you what to do. That means that when you're looking at these dimensions, when you fix the Sauner symmetry that you want, you choose the representation by insisting that you should diagonalize one of the cyclic subgroups in the Heisenberg group, which is a singlet under the symmetry. Because the Sauner symmetry now transforms the elements in the cyclic subgroups among themselves, that also means that it will transform its eigenvectors. There are eigenvectors among themselves, which simply means that the symmetry operator will be a permutation matrix, provided the dimension is 1 mod 3. And as it happens, in the sequence n squared plus 3, all the prime factors that occur, except sometimes 4 occur, but this is relevant. If the dimension is n squared plus 3 and prime, then the dimension is necessarily 1 mod 3, the prime, and that means that our symmetries will be represented by permutation matrices. This is basically why it works. So what you do is that once you have this permutation matrix that leaves a seq invariant, then you can also find a Clifford which has this property here, which will generate the set of matrices in the Clifford group that commute with this thing. And this UG will be a permutation matrix as well. So when you apply this permutation matrix to a almost flat vector like this, you will simply have the effect of permuting these phase factors. On the other hand, the Galois group of the small ray class field, in which these things are square roots of Stark units, is also cyclic. Dimension is prime for the moment. And all you have to do to construct the seq is to match these actions, and then you have it. It always works. Well, I think. There's a similar reason why some of these ladder constructions that I discussed earlier are simple. So the reason why the ladder starting from D1 equals to 5 is as simple numbers occurring in it is related to this fact as well. Because if you look at the dimensions that will occur in this sequence, their prime decomposition is always like this, where all the prime factors are necessarily 1 mod 3, except the first, which is a bit of a bother. But all the others, as you go up the sequence, you're going to have a simple permutation action of the symmetries. That's basically why this is simple. I should say that when I find things like this, my standard method of solving number theoretical problems is always to ask a person called Gary McConnell, and he usually gives the answer. As surprisingly often gives the answer. It's a bit tricky to prove. What was on the next slide? Aha. And now we come to the topic of my talk, I think. And it's almost over, but yeah. So factors of 4.
10 minutes.
Factors of 4. Factors of 4 in these prime decompositions will be a bit of a problem. If you're looking at these ladders here, if D is odd, so the next, if you know the seq in dimension D, you're trying to construct this seq in dimension D times D minus 2. If D is odd, D and D minus 2 are relatively prime. That means that the Heisenberg group splits as a direct product. The Hilbert space splits as a tensor product. You can use elementary entanglement theory to get around. So it's rather simple. If, however, these dimensions, the starting dimension is even, then clearly these D and D minus 2 will no longer be relatively prime, and that's a problem. You sort of have to remove a factor of 4 from this thing before you can apply entanglement theory. So factors of 4 are a bother in this kind of thing. In this other infinite sequence that I talked about, one can prove that the prime decomposition of a dimension in the sequence is always possibly a factor of 4, possibly a factor of 3, which is not too bad. And then all the other factors are primes mod equal to 1 mod 3. So permutation action occurs, applies here. But if you're looking at even dimensions, we're going to have a problem with a factor of 4 here, which destroys the permutation property in the standard representation. There's another reason to be interested in dimension 4, etc., which is that an irritating thing about this business, if you're interested both in mutually unbiased basis and seeks, is your first question is, what do they have to do with each other? Now, if the dimension is a prime, they have a lot to do with each other because they basically constructed from the same group. However, if the dimension is not prime, MUBs use a different Heisenberg group. In prime power dimensions, there are 2 different Heisenberg groups. Seeks use one of them, MUBs use the other, and so it seems that MUBs and Seeks in prime power dimensions have nothing to do with each other. Well, this person has just solved this problem in dimension 4. I'll come to that. And here's a Heisenberg group for dimension 4. I've listed I've put all the elements, and I tried to make it look like a flower, but I failed. So here's a cyclic subgroup of order 4. Here's another cyclic subgroup of order 4, but they no longer disjoint. They meet here. And here's another cyclic subgroup, and it meets this one instead, etc. So there are 6 cyclic subgroups of order 4 here, and under Sauner symmetry, they mix like this, meaning that there is no cyclic subgroup of order 4 that is left invariant by the Sauner symmetry, meaning that you can't represent. If you choose to diagonalize one of these cyclic subgroups, there's no way you can get a permutation action for the Sauner. So it's going to be much more complicated than primes mod 1 equal to 1 mod 3. But if you look at this picture again, you realize that there's another interesting abelian subgroup here, namely the one formed by these 3 elements here, plus a unit. This is a special subgroup, maximal set of commuting variables, if you like, consisting purely of order 2 elements. Under the Sauner action, they transform into each other, meaning that the eigenvectors transform into each other, meaning that if you diagonalize these 3, the Sauner action will again be given by a permutation matrix. So this is a basic trick by means of which you can get a much simpler view of what happens in dimension 4. So we're going to use this subgroup to define the representation. And the symmetries of the seek are now given by permutation matrix. Once you've made this observation in the D equals n in this infinite sequence, means that suddenly everything works as before, basically. That's why we were able to, and moreover, you get some bonuses. It turns out that the number fields you encounter when this is even are actually somewhat easier to treat for some reason than those that occur in the odd case. So actually, in this infinite sequence, I think for the first time in the seek story, even dimensions are much easier to treat than odd dimensions, or easier to treat than odd dimensions. And this happens because you can play this trick in the dimension 4 factor. The ladder story and dimension 4 is a little bit more complicated and requires a bit more work, but that work has been done by, among others, the next speaker, I think, and also by these people, Andersson and Dumitru. Yeah, and I think that's more or less the end. But I should talk a little bit about the other. So this is really where my talk was supposed to start. So here's the other Heisenberg group. This is the Heisenberg group we use for seeks. It's a very relevant Heisenberg group. People in signal processing always use this one. Here's another. And because 2 and 2 are obviously not relatively prime, these are different. This is the other Heisenberg group in dimension 4. This is the one that is relevant to MUBs and also for quantum computers and all sorts of things. And also to our shaman. Right. Although he prefers dimension 8, but it's the same story. But now these groups are, although they're distinct, they're actually very closely related. You see, in this group, all the elements are order 2. And now, when we treat this group here, I said we should focus on those elements that are of order 2. So what we can do now is that we can identify this unique abelian subgroup in this group to any one of the maximal abelian subgroups of this tensor product group. So we could identify this subgroup of that with this subgroup of that. And then what one finds is that the group elements here, so now these groups are firmly tied together. And then what one finds is that this group here is actually a subgroup of the Clifford group of this thing. Conversely, this group is actually a subgroup of the Clifford group of that thing. So that enables a rather firm link between Siegs and MUBs in dimension 4 to be made. But it says now that I have presumably run out of time now, so that's the end. Thank you.